Okay, it's Mr. Masseroni back in our mathematical lair here, and with another video. We're going to be talking about mathematical induction. Mathematical induction is a way of proving statements, okay? And I'm going to tell you exactly what it is. It's the same process every time, okay? I'm going to go through that process with two different examples, but it's the same process, and I'll point out to you what stays the same in every question, okay? What it is given a statement involving a positive integer n. Okay, if the statement is true for n equals 1, and the truth for n equals k implies the truth for n equals k plus 1 for every k that's greater than 0, then the statement is true for all positive integers n. All we're doing here is changing the variable to k, and then saying if it's good for k, it should be good for k plus 1. If it's good for k plus 1, it's good for every integer after that. Okay? Now here's how we set the proof up. First thing I have is I want to prove that 3 plus 6 plus 9 plus on and on all the way up to 3n. So basically all multiples of 3, when you add them up, it equals to 3/2 n times n plus 1. Now n, as always, is your number of terms. Okay, it could be a 4, could be a 5, could be a 9. It doesn't matter, whatever number you put in there. If you add up all those terms on this side, and then you plug the number in here, these should be the same. Now the first thing you do is we must show that it is true for n equals 1. That's always your first step, okay? Always first. All right, so what we do is we do n equals 1. In the left side, we only have the one term, so it's 3 times 1, and that has to equal 3/2. We put the 1 in for n, and 1 again, 1 plus 1. So 3 times 1 is 3. 3/2 times 1 times 2. You cancel out. These are fractions. If you make them fractions, you reduce. 3 equals 3. Check. That's step 1. It's always the first step. N equals 1. Now, you actually write this statement. We are going to assume that n equals k is true. All we're doing there is changing the variable, okay? And show, n equals k plus 1, okay? So what we do is we assume that 3 plus 6 plus 9 plus on and on plus 3k equals 3/2 k times k plus 1. We just changed the variable. We assume that that is true. Okay? We must show that 3 plus 6 plus 9 plus and on 3k plus 3k plus 1. Okay, we're going to the next step. If we can show that these are the same, that will continually work. So instead of k, okay, back in our original equation, instead of k plus 1 times k plus 1 plus 1. Okay? I'm taking it to the next step. We assumed it's right for k. We changed the variable from n to k. We assumed it's right. Now I'm just going to take it to the next step. Okay? Now we've already shown by assumption, I went too far there. This piece right here is 3/2 k times k plus 1. This comes from our assumption. Okay? So we have that plus 3 times k plus 1 has to equal 3/2 k plus 1, and I'm just going to go to k plus 2 there. Okay? Is everybody following along, I hope? Now, what you're looking for, essentially, is to make one side the same as the other. And what I'm going to do here, I'm just going to expand it and combine my like terms. Okay? So 3/2 k times k is 3/2 k squared plus 3/2 k plus 3k plus 1. Okay, I just distributed 3/2 k times k, 3/2 k times 1. And then I'm adding 3k plus, check that, plus 3. Sorry about that. And if I combine it all together, 3/2 k squared plus 3/2 plus 3 is actually 9/2 k plus 3. Now I'm hoping the other side's going to do the same thing, and what I'm going to do is I'm going to leave the 3/2 k and I'm going to distribute my binomials. And I get k times k is k squared plus 2k plus k plus 2. Simple FOIL. Okay? Now I distribute the 3/2. 3/2 k squared. Now this 2k plus k gives me 3k. 3 times 3/2, 9/2 k. 3/2 times 2 gives you 3. And if you look, they're exactly the same. Okay? That's what you're doing. This piece right here is what changes. You're always doing this here. We're going to assume, and then your equation, okay, and then you have to show the k plus 1. And then you have to manipulate. Now you have to give your final statement, okay? And that is, since we showed that the statement is true for n equals 1 and n equals k implies n equals k plus 1, that's how you word it, then we can conclude by induction that it is true for all n greater than or equal to 1. Okay, now going back up at the top, this piece right here is always there. Here, this piece here is always there. All that changes is the equation. This piece here is always there. Okay, those three that I starred right there are always the same when you do an induction proof. All that changes is what your equation is when you substitute for 1, when you do your work in the body here. Okay? I'm going to do another example for you. And if you need to, you can go back and look at these again, work through them, see how they go. Okay? This one's a little more involved. Okay? And what I have, prove that n squared plus, in parentheses, 2n plus 1 equals n plus 1 squared. Okay? We will do a proof by induction. First, we must show the case is true for n equals 1. So I'm going to substitute ones in where all my n's are. So I have 1 squared plus 2 times 1. Ooh, close my parentheses a little early. Plus 1 equals 1 plus 1 squared. So we know 1 squared is 1. 2 times 1 is 2, plus 1 is 3. 1 plus 1 is 2, squared is 4. 4 equals 4. Check. There's our first part. Okay? Now, we will now assume that, and all I'm doing is changing the variable, k squared equals, check that, plus k squared plus 2k plus 1 equals k plus 1 squared is true. We assume that's true. We must show that k plus 1 squared, now I'm just putting k plus 1 in where the n's were, plus 2k plus 1 plus 1 equals k plus 1 plus 1 squared. Okay? We have to show that. Now, we must show that that is true. Now, I'm going to move it down. I'm going to condense all these k plus 1s. Okay, give you some space. K plus 1 squared plus, I'm going to distribute this out. 2k plus 2 plus 1 gives me 2k plus 3 equals k plus 2 squared. Okay? Now, k plus 1 plus 1, oh, check that, k plus 1 times k plus 1 plus 2k plus 3 equals k plus 2, k plus 2. I just expanded the squares to make this a little easier. Now I FOIL, and I get k squared plus k plus 1, right? K squared plus k plus 1 plus 2k plus 3 equals k squared plus 2k plus 2k plus 4. Okay? Just expanding your binomials. Combine all my like terms. K squared, 1, 2, and 2 is 4k. 1 and 3 is 4 equals k squared. 2 and 2 is 4k plus 4. And it checks. That's exactly what we're looking for. So, we go to our last point. Since we showed the statement is true for n equals 1 and n equals k implies n equals k plus 1, we can conclude by induction that it is true for all n greater than or equal to 1. Okay? And that's the whole thing. There's 2 examples there. If you want, when we get together, there'll be more. I have another example. I'm sure Mr. Higgins has examples. Ask questions, send emails, whatever you have to do. I hope everything's going okay for everybody. And I look forward to seeing you guys in class. Thanks and good luck.